Hello. In this video, we want to look at the layers of Earth's interior and kind of how we know that they are what they are. So we've got the Earth split into kind of three distinct layers. First is the crust, the uppermost layer, and then the mantle, the middle layer, and the core, all the way to the center. I'm going to look at each one of these in a little bit more detail. So the crust is made up almost entirely of rock and can be split into two major categories: continental crust and the oceanic crust. So continental is just what it sounds, underneath all of the land masses. And so it kind of vary in thickness, but on average it's about 35 kilometers thick, and it's got a lot of variation in material, all sorts of different types of rock in the continental crust. The oceanic crust, like it sounds, is underneath the oceans, and it's between 5 and 12 kilometers thick on average. Again, there are way thicker spots and way thinner spots, but on average 5 to 12 kilometers. And it is more dense and less varied than the continental crust. Okay, there are fewer types of rock in the oceanic crust. It's worth noting that it's kind of easy to get backwards, that the oceanic crust is different because that's where the oceans are, but really the oceans are there because the crust is different, and it is denser, like I said, so it actually sank down more into the mantle than the continental crust did. And so just naturally being more dense and being sunk down lower, that's where the water went to. Okay. So that just being more dense is what caused the oceans to be where they are. Next up, we've got the mantle, again made of rock, but it's now semi-solid. Okay, it's getting hot enough as we go down. As the farther we go down, the warmer it's going to get. And now this rock is hot enough that it can shift and it can move. The mantle overall is about an average of 2,900 kilometers thick. Again, that varies quite a bit. And the deeper we go, the hotter it gets and the higher the pressure is. Right at the base of the crust, we're looking at about 1,000 degrees Celsius, and then that just increases the farther we go, all the way up to about 3,500 degrees Celsius at where the mantle meets the core. Mantle is where diamonds come from. Okay, so they're formed down there in the presence of all that pressure, and then they come up in the lava flows, where they did come up in the lava flows. Next up, we've got the core. Rather than being made of rock, it's almost entirely made of metal. And we can split that into the outer core and the inner core. The outer core is about 2,300 kilometers thick, and both the outer and the inner are mostly iron and nickel. So, like I said, made of metal. And looking at about 3,500 degrees Celsius in the outer core. It is liquid at that temperature. That metal is liquid at that temperature and pressure. The inner core has a diameter of about 1,200 kilometers, so all the way across, 1,200 kilometers. Again, iron and nickel, and the temperature is even higher at about 5,000 degrees Celsius. One kind of interesting thing is that being even hotter, it is now a solid. We've gone far enough down, there's enough material pressing on it that its pressure is high enough to actually make it a solid, even at that higher temperature. So we've got the core as solid. One thing to note, this excess temperature, it's from friction and radioactive decay. Okay, so there's a lot of radioactive elements decaying in the core, producing all this heat, and then friction of the molten material moving around. You can see from the picture there's a couple more kind of classifications of these layers. First is the lithosphere, which includes both the crust and this uppermost layer of the mantle, which is solid and brittle. Okay. And then it's divided into sections, the tectonic plates. So together, the crust and this uppermost layer of the mantle make up the lithosphere. And then right below that is the asthenosphere, which is this molten portion, or semi-liquid portion of the mantle, which is where most of the movement from convection happens that leads to the tectonic plates shifting. That'll be talked about more in other videos. So kind of a natural question of how do we know what these layers are made of, because we haven't been there. The deepest hole on Earth is only about 12 kilometers deep, and that was a man-made hole, kind of a project to try to drill through the crust of the Earth. They missed it by a little bit. They didn't quite get through the crust, but still 12 kilometers versus the radius of the Earth, 6,300 kilometers. Okay, so we're nowhere close to actually having seen or taken samples or anything from any of these other layers. So the question is, how do we even know what's down there if we haven't seen it, if we haven't been able to sample it? First thing are some surface rocks. What came up in the lava flows can kind of give us an idea of what the mantle is made of. So just through examining lava flows and current and old, we get an idea of what the mantle must be made of. We also get some insight from meteorites, okay, because if a meteorite has certain materials in it, then it's a good bet that they might be part of Earth's interior as well. So meteorite probably came from some other body breaking up and coming to Earth, so we can examine what it's made of and see if that matches what we know about some of the materials that might be in Earth. Another way is seismography. We'll talk about this a little bit more in depth, but it's all about how waves travel through different materials and how scientists have been able to record and study how the waves travel, typically waves due to earthquakes. Gravity is another way that we can kind of narrow down what some of the materials must be. I'll talk about that again here in a minute. Same with magnetic fields. We'll touch on that again. First off, these seismic waves, they're all about waves created by an earthquake and how they travel through the different materials. Okay, so we'll talk about that in a little bit more detail here. First, when we have a wave traveling through materials, it either be a compression wave, which is kind of back and forth like this. If you imagine grabbing the slinky and pulling it back and forth, we're going to get waves that travel back and forth along the direction the wave is traveling. And then there are shear waves, which travel up and down based on the direction of the wave. Up and down or side to side. They don't travel along the direction of the wave. And studying these in different materials, we get these P waves, which are these compression waves, primary waves. They, in general, they travel faster. Through any material, they travel faster than these secondary waves or the shear waves, which is how they got their name. The primary waves are observed first, and then the secondary waves afterwards. So this table is just the speeds of these two types of waves in different materials. And so there is some variation, but in general, primary waves travel faster than the secondary waves. And so by measuring the waves caused by earthquakes, we can kind of narrow down what materials must be under the surface of the Earth. And we can look into this in more detail, but primary waves can travel through any material, solid or liquid, and so they can travel straight through this the liquid outer layer. And secondary waves are stopped entirely by liquid. So that's one major clue as to, and this was done in the 1920s, so it's all relatively recent. But this is one way that we can narrow down that there must be a liquid core, because over all the years of measuring seismic activity, there's just places where you can't get these secondary waves where you do get the primary waves. Another way to narrow down the materials is as these waves, I'm not going into a lot of detail, but as these waves travel through different materials, as they go from one material to another, they're going to refract just like light waves do. And so by figuring out where we can measure the waves at, we can kind of narrow down what materials they must have traveled through and whether or not some of them reflected off of the solid core that were showing up in places where we didn't expect them to. So just by mapping out how these waves travel and where we can read them at based on where we're at on Earth and where the earthquake happened, we can really narrow down what the materials are below the surface. So to get back to gravity a little bit, so Isaac Newton was able to calculate the mass of the Earth, and based on that mass, it wasn't making sense that everything that we could observe on the crust was not dense enough to give us that mass. So based on that, we kind of had to infer that there was something heavier inside of the Earth, so namely metal. Then I kind of talked about convection earlier also. So with this, with the center of the Earth being the hottest and then cooling as we go farther away, there are kind of convection loops just like there are in air, with the warm air rising and then sinking back down to the ground and warming back up. So inside of the Earth, this convection, as the material gets closer to the center, it heats up, which makes it move away from the center, rise to the rise through the liquid to the outside, and then as it gets to the outside, it cools back down and comes back. And this movement actually generates the magnetic field of the Earth. And this wouldn't be possible if there wasn't metal in the center of the Earth. Okay, um, even in its liquid state, the movement of the the molten outer core generates an electric field. So between all of those, we're able to narrow down whether or not the layers are made of rock or metal, and whether or not they're solid and liquid. So very brief overview, not a very in-depth description at all of what was going on. But if we get back to the layers here, kind of a quick overview of everything. We got the crust, which is very, very thin compared to the rest. The mantle, which is still made of rock, but in a semi-liquid state. Okay, so it can flow and it can move. You've got the core split into two sections, all metal, the outer being liquid and the inner being solid. And as we talk about primary waves from these compression waves, the primary waves from an earthquake, they can travel through the solids of the mantle and the crust. Once they get to the liquid outer core, they slow way down, but they do pass on through, and we can read them on the other side of the Earth. The secondary waves, they can pass through the crust and the mantle being solid, but as soon as they hit the liquid outer core, they stop entirely. So they can't be measured outside of that whatever angle. So, real quick overview, but kind of the basics of the layers of the Earth and how we were able to narrow them down.